Cool. Hi, welcome back to discussion. So just to start off, the only announcement is congrats on finishing the midterm. Really good job on that. I know like 188 midterms can be super difficult, and I can only imagine like taking it online must have been like even harder. So yes, like good job on that. Now you got through. There's only one midterm for this class, so there's like a while to kind of chill and relax in terms of different tests. And yeah, so now moving forward with the next topic in this class, which is BayesNet. So specifically in today's worksheet, we will be focusing on how to draw and use BayesNet to represent different scenarios or different situations. And then we'll also be doing some like probability questions to get more familiar with computing different forms of probability. Cool. So to start off, just like a quick mini lecture on BayesNet. So I'm actually going to point out some things about probability first. So with probability, there are things that we call random variables. And random variables are essentially events whose outcome is unknown. So since the exact outcome is unknown, we will usually represent random variables with the probability distribution. And essentially a probability distribution includes an assignment of weights, or you can also think of them as probabilities. So I'm just going to abbreviate with probs for each outcome. So a simple example is you can have like a random variable x that represents if you flip a coin whether it is heads or tails, and then your probability distribution will be 50% or 1/2 for heads and then 1/2 for tails. And then something that we tend to look at regarding like random variables and probabilities is the joint distribution. And the joint distribution essentially considers two or more random variables and specifically their probability distribution. So an example of a joint distribution is usually represented by like a bunch of random variables separated by commas. So just kind of, they would look like probability of x and y, for example. And also something I want to point out is that I am used to writing the P of probability with this like double line. I'm not quite sure where I picked it up from, but just to let you know, I will be writing probability that way, and I think it's like a good way to differentiate between just like the P variables. But just wanted to point that out because I know it's like weird and I don't want you to be like, oh, what symbol is that? Cool. And then the last thing regarding probability that I want to point out is the difference between independence, specifically between marginally independent, which is just when two variables are random variables are independent. So like x is independent of y, and this middle symbol just represents independence, versus what we call conditionally independent. And conditionally independent is when two variables are independent given a certain variable. So we can just say given z. So these are terms that we want to keep in mind in regards to probability. But cool, so now let's actually go into more of the basics of what a Bayes net actually is. So we can say Bayes net here. And how a Bayes net looks like is that we have the situation where each node is going to be equal to, let me actually zoom in a bit. So each node is going to be equal to a probability table of the variable given its parent. And this notation might seem a bit confusing first, but we're going to go through some examples and I think the format will become more obvious. And in terms of putting the whole Bayes net together, it will essentially be a DAG, which is just a directed acyclic graph. So a directed graph, so there's like arrows instead of just lines, and then there are no cycles in this graph. And it's a directed acyclic graph of probability tables, like the one that each node represents. And the whole point of having this DAG of probability tables instead of just one big probability table is because of memory. Like, we don't want to store all the different possibilities in this like huge table and have to look it up every time. We want instead a more memory efficient way of sorting it. So that's why we have this DAG of smaller probability tables instead. Cool. And then the main thing we want to remember about Bayes net are these two really important traits. So let me actually move these pictures up. Cool. So the first thing that we want to remember is that for Bayes net, so I'm just going to call this the first thing, each node is conditionally independent of all its ancestor nodes, which essentially just means not their descendant, but anyone that above them, given all its parents. So, for example, in this case, the variable x is the main variable we are looking at, and it's conditionally independent to any of its ancestor nodes. So I am just going to pick ui, but it can also be um or anything above that, given all its parents. So its parents currently are u1 and um. So that's an example. Cool. And then the second main trait is here, and it is when each node is conditionally independent. So keep in mind that both of these situations are conditionally independent, not just marginally independent of all other nodes given its Markov blanket. Markov blanket. And a Markov blanket will essentially consist of the parents plus the children plus the children's other parents. So essentially everything like wrapping it, which is why in this picture here, we see that it's like the whole circle wrapping it, like the parents of the different arrows going into the z's, or specifically the z's going into the y's, because the y's are the children of x, are also included. So that is what a Markov blanket is, and in that case it can be true for any of the nodes, not just the ancestors. So for example, something we can write here is that x is independent to y1, for example, given the u1, c, lj, t, nj, y1, and yn, and so on, depending on everything else. I'm seeing this now, but I think this is not supposed to be a parallel sign. Sorry about that. It should just be given, so one line. I think I accidentally just wrote 2. Cool. So these two are the main Markov, the main things you want to remember for Bayes nets. So we really want to keep those in mind. Cool. Yeah, so that's pretty much it for the mini lecture. So now I'm going to shift more to the actual problems on these worksheets. So let's just scroll down. So in the first question, we have this Bayes net right here. And we can see that there are like 7 nodes, and we have some like directed edges. And remember that for each directed edge, if it goes from like A to B, that means that A is influencing B in some way. Cool. Now the first thing we want to do is to write out the joint probability distribution. So let's first consider what different factors or like information from the nodes in this Bayes net that we have, because then we can use those factors and then multiply them together in order to get the overall joint probability. Cool. So in a Bayes net, all of the probabilities, remember, are the current node given its parent. So based on that, we can kind of first write out the different factors that we have. So we can just start with A and go alphabetically. So we have the probability of A, and there's no parent, so it's just A. For B, it has one parent, which is A, so B given A. And then for C, similar situation. And then now let's look at D, who also only has one parent, specifically given B. And then we also have E, which has no parent, and then F, which has 2 parents, so then we are given D and E, and then probability of G given D, because D is G's only parent. Cool. So these are the factors, and whenever they ask for like the joint probability distribution of all the variables, all we need to do is multiply the factors together, and that will be equivalent to the joint probability. So specifically, we can say like joint prob, let me actually write it out in terms of variables. So probability of A, B, C, D, E, F, G will be equal to all of these factors summed up. So if I write it out, it can be in any order. So probably A, B given A, and this is all times C given A, D given B. I don't know why I suddenly wrote an F, but probability of E, and then probability of F given D, E, times probability of G given D. Cool. So that will be your resulting answer for what the joint probability is. So essentially all the factors multiplied together. And we got that factor by looking at each node and seeing what the parent nodes were. Cool. So then now we want to look at the nodes A, D, and F and determine how many entries there are in the tables, given that each node can take on 4 values. So that means for each node we will have 4 options. So the best way to determine is for these nodes what the table would be, and then we can get the number of entries based on how many nodes there are, because we know for each node there will be 4 values. Well, so we can look at the factors that we wrote before, and we see that A was just the probability of A. So that means that there's only one node, so it can only take on 4 values. While if we look at D, we see that the probability was D given B. And since there's 2 values, so in your entry table you will specify both what the D value is and what the B value is. You have 2 variables and each of them can take on 4 values. So because of that you have 4 options for the first one and then 4 options for the second one. So that will become 4 squared. And then we can look at F, which is going to be F given D and E. So now 3 variables. So that will become, right, this is a straight line, that will become 4Q. Well, so then based on that, the number of entries that we have are 4 for A, 4 squared for D, and 4 cubed for F. And that will be your answer to part B. Cool. Yeah, so then now let's actually start looking at some values for the probability distribution. So we are going to take a look at the different values that are given in these tables for A, B, C, D. And we specifically want to determine which variables are independent to each other and which are not. And they want us to just look at non-conditional independence, so essentially like there won't be like a given something, just like whether each variable is independent or not to all of the other variables. Cool. So we know when we consider independence, the value shouldn't affect the resulting probability distribution. So for example, if A is independent of B, then the probability of A should be equal to the probability of A given B. Like knowing what B is shouldn't affect it. And yeah, and kind of in a similar way, that's also why like when you have a probability that is independent, then you know like probability of A and B, the joint probability, will just be equal to probability of A times the probability of B, because they are both not affecting each other. Cool. So to see here, the best way to judge these tables is whether we have the situation where if A is positive, we will get the same values given the other one no matter what, and vice versa. So we can see by looking here that we get some of the same values in terms of when we do like plus B minus C, we get 0.2, minus B minus C, we also get 0.2. And then here we have the same thing for the 0.8. Cool. And then here we have a situation where minus C, no matter what D is, will give you 0.5, but not the other way around. Cool. So kind of based on these, we can point out what variables are not independent with each other, and then we can deem the rest to be independent. So for example, we can see that A is not independent with B. And that's because if you look at this table, for instance, the probability of, if you flip it around, B given A should be the same when you have plus B. Like no matter whether your A's are minuses or not, you should have the same probability. And that's because if you write this in like the flip way, you can get probability of B should be equal to probability of B given A. So even if you take A into account, it shouldn't matter and shouldn't affect whether A is positive or not. It should still be the same probability. But that's not the case here because we have 0.9 and 0.6. So we can tell that A is not independent with B. And a similar situation happens with C and D. So we know that C is not independent with D because if we look here, both of these situations, we have positive C, but the values are different. So because of that, C is also not independent on D. And you can go through and check the other ones as well, but these are the only two values that differ. And then so because of that, you can just directly write out that, for example, A is independent with C and with D, and then B is independent with C and D as well. Cool. And then you have all the 6 different relationships between the 4 variables. Oh, yes, so this will be your resulting answer. So essentially you want to look at the probability distribution table and then consider like what independence means and how the probability should be the same or different based on that. Oh. And then now let's move on to part D. So in part D, we are given a whole new scenario and a bunch of these different variables. And our goal is to be able to draw out the Bayes net. And I think this is very important because it kind of bridges the divide of going from like a word problem to actually using like the mathematical implementation to represent it. So we won't end up doing any calculations really on it, but it's a good tool to know how to draw the Bayes net given a word problem. So yeah, let's go through this. So specifically, we're building advanced safety features for a car to see if they are falling asleep and to calculate the probability of a crash. And you have these 6 sensors, so E, W, L, S, H, and R, and there's a description for each of these. And specifically, we see that A is influenced by these 5 variables, and C is influenced by these 4 variables. Oh. So in a Bayes net, to be influenced by something, that means you must have an edge between them. Specifically, you will have an edge from the influencer to the person that is influenced. So then based on that, if we come down to kind of this like nodes that we see here, we can start drawing the edges. So we see that A influences E, so we can draw a directed edge to E, W, H, L, and C. And then we also see that C influences A, S, L, and R. Cool. So now we have to start kind of consider, oh sorry, I read that wrong. It says C is influenced by A, S, L, and R. So that means there is an edge going from each of those 4 nodes to the C node. So we already have the A edge, so we can just add the S edge, and then the L, and the R. So we will ultimately get this graph where we have like everything kind of pointing from the top to one of the nodes on the bottom, except for like the L to C node. And that'll be how you represent it. I think usually they won't distinctly tell you as much this line, so that would be like what you're interpreting the most. But given for this one, I think we want to just focus on the translation, which is why like everything was given super explicitly. Cool. So that basically wraps up the problem 1. And now we will move on to problem number 2, which is more probability focused. And it's specifically how we are given this Bayes net and these like probability distribution tables, and we want to use these values in order to calculate different probability values. So the general like storyline is that patients can have a symptom S, and it can be caused by 2 different diseases, disease A and B. And it is known that a specific gene has a big role in causing disease A. And then here we have our Bayes net and the corresponding probability distribution. Cool. So in all the subparts of this problem, we will be given like a kind of probability expression, and we want to determine how we can use our factors together in order to figure out what the value is. Now, if we remember from 1a, when you have a joint probability of all the variables in the Bayes net, you essentially have to multiply the different factors together. And we know what our factors are. They are PG, PA given G, PB, PS, S given AB. And even if these probability distributions weren't given, we can still figure them out by just looking at the nodes and what their parents are. Cool. So specifically here, when the variables in the probability are lowercase, so like in here, they are already assigned a specific value. So you want to be calculating the value based on that instead of just on the random variable, which if I actually forgot to mention this before, but with random variables, your like letter is always capitalized. So that's how you know it's a random variable. And then when it's an actual value, it will be lowercase. So that means we want to multiply our factors together specifically with these values. So that means we want to multiply probability. We can take plus G and then times probability of plus A given plus G. And going to the right side, we have probability of plus B and then times probability of plus S given plus A and plus B. And then now we can plug in the actual values for this, and then specifically we will end up getting, I believe it is 0.1, and then times 1.0, and then times 0.4, and times, so we go plus, all of them are plus, so we just times 1. So we will end up getting 0.04 as the answer to the subpart. And then let's move on to part B. So now we want the probability that a patient has disease A. So we want to think about what we currently have, which is P of A given G. So a common way in order to sum up the probabilities if it's given a variable is to just sum up all the possibilities of the other variable. So we know that G can either be positive or negative. So that means we can set this equal to probability of positive G times probability of positive A given positive G plus probability of negative G times probability of positive A given negative D. And this is actually called the total probability rule. If you took 70, this should be gone over. But in general, I think the intuition is also pretty sound in how you want to consider the different possible cases and then add them together. Well, so we can plug in the actual values. So you have 0.1 and then times when they're both positive, which is 1.0, plus 0.9 times when A is positive, G is negative, which is times 0.1. And then if you add this together, you will get 0.19. So the probability that a patient has a disease A is going to be 0.19. And then part C, we want the probability that a patient has disease A given that they have disease B. Cool. So whenever you have these kind of given scenarios, you want to see whether the two variables are independent or not. Because if A and B are independent, then the probability of positive A given positive B will just be the probability of positive A. And this is kind of like a hint too, especially if like a previous subpart asks for like the probability already. You want to make sure to kind of like strategically check for independence first versus just like going through like all the calculation. So yeah, so let's scroll up and see. So here we see that both A and B go to the same children, and they are affecting the same children, and they don't have any common ancestors. So in general, if there are no common ancestors, two nodes will be independent. And that's because like there isn't something like even in their whole past that like influences both of them. So it is understandable how they are independent then. And there's going to be like a more rigorous mathematical proof about it that will be gone on later in lecture, but just kind of like thinking about it, since no one or nothing will influence both of them, they are going to be independent. So because of that, since A is independent with B, then we know that this is just equal to the probability of plus A, which we already calculated in part B. So that is just going to be equal to 0.19. And specifically, that is because A is independent with B. Oh. So yeah, good thing we don't have to recalculate it. And then now moving on to part D. So we want the probability that patient has disease A, but instead of just being given disease B, now we are also given disease S. And symptom S. So the first thing we want to do is kind of similar. We want to check if A is independent to S, because if that is the case, then it would just still be the probability of A, because giving like kind of, you can think of them as like random other values won't influence your probability. So let's scroll up and see. So here we can see that A and S are not independent because A is essentially directly influencing S. So S will be something based on A or be influenced by A. So we can't use our tactics since the two are not just independent. So let's kind of think of different ways in order to represent this first. So a good kind of probability trick, whenever we have given probability, is to kind of consider the situation where all of them are true versus like the different options. So what that means is that we can take the probability of plus A, plus S, and plus B. So the joint probability. And then we can divide by the situations where we may not necessarily have plus A, but we are sure that plus S and plus B are true. And how that is represented is through probability plus A, plus B. Oh, sorry, I put S first, but just so it's in the same order. Oh, wait, I put the same S on top. So plus S plus B, and then we want to add that to the probability where it is not true. So essentially we are just kind of looking at all the situations versus when A is positive, but we are taking S and B into account because we are conditioning on that. Cool. So we have kind of gone over like how to write like the joint probability, and essentially want to multiply all the factors together that have those variables in it. So we can do that, and then like on top we had probability of A, so we be plus A, and this was specifically calculated in part B and then used in part C. And then we also already have probability of plus B just from the diagram above, since B has no parent. And then we want to multiply that by a probability of plus S, and remember that was given plus A and plus B. And the denominator, this first term is going to be the same. I am kind of running out of space, so I'm just going to do like double quotation, but just keep in mind that means like the same term as this expression on top. But then we want to add to it the negative version. So what that happens is we're just going to do negative A instead, while everything else stays the same, except for here negative A again too. Cool. And then now we have all of these values, so we can plug it in and actually solve for what this probability is. So the value specifically will be, I think, 0.19 times 0.4 and then times 1.0. And you have those three multiplied together again in the denominator. And then you specifically want to add the negative term, so then it becomes 0.81 times 0.4 and then this is 0.8. And then if you simplify this will be about 0.2267. So that will be your solution for part D. So yeah, that would be your probability that your patient has disease A, given that they have disease B and symptom S. And then moving on to E, the last part. So now we want the probability that the patient has gene variation G, given that they have disease A. So a probability of positive G, given positive A. And usually when it's a situation where you have you want to calculate one variable given the other. And similarly, we can first check whether G and A are independent or not. For a similar reason as A and S, there's a direct edge going from G to A, so you know that they can't be independent. Cool. So then based on that, a good way to usually calculate a situation where you have a variable given a variable is with what we call Bayes' rule. And specifically that has been mentioned about in the past before, and if we apply that formula we will get the situation where we have probability of plus G times probability of the opposite condition, so plus A given plus G over the sum of plus A. And we can same thing, right? Probability of plus A out in total probability rule, but if we just look back on a previous subpart, we can see we already saw for that kind of denominator value in part B, so we can just directly plug in 0.19 for the value. So a good trick with probability is that they usually build or kind of utilize previous subpart information, so it's a good thing to regularly check back and to make sure that you incorporate information, or if it helps simplify calculations, or if it helps you not have to do extra calculations, make sure to look back and check for different subparts. And that means we can just plug in the values, and we know that the bottom is just 0.19, and then the top will be, if we look at positive G, that is 0.1, and then times 1.0. So this will eventually get us to be equal to 0.5263, and that will be your solution for this subpart. And then yeah, that is it for the rest of this section, and hopefully you did well on the midterm and had fun with the midterm. I remember when I first took the 188 midterm, I thought it was really fun for some reason. Not quite sure why, but I think it was just super interesting. So hopefully that was a decent or a pleasant time. But yeah, thank you for watching this discussion.